What is non-uniform circular motion? Unlike uniform circular motion, where the speed of the particle remains constant, in non-uniform circular motion, speed changes as well. So that means the velocity of the object not only changes in direction, but changes in magnitude. So we know that in order to maintain an object in a circular path, there always needs to be a centripetal force or a force directed towards the center of the circle. It is this force that is going to keep the object moving in a circular path, preventing it from going off in a straight direction in its tangential velocity. But in non-uniform circular motion, in addition to the centripetal force, there will be a tangential force or a tangential acceleration resulting from the tangential force. So that means there's going to be some component of the force acting either in the direction of the velocity or opposite to the direction of the velocity. So non-uniform circular motion will have two accelerations, or two components of acceleration: a centripetal acceleration, which changes the direction of motion and keeps the object in a circular path, and a tangential acceleration, which is responsible for the change in the speed of the particle as it moves in the circular path. So the net acceleration for the particle is the vector addition of the centripetal and the tangential acceleration at any instant. So let's look at an example. So if you take an object and tie it to a string, a mass tied to a string and whirled in a vertical circle is an example of non-uniform circular motion. So let's see how. So here is a ball that is tied to a string and it is whirled in a vertical circle like this. So let's look at the ball when it is in this position. What are the forces acting on the ball? There is gravity, which is straight down, and then there is the tension that acts along the string. Now we want to know what is the centripetal force that is acting on the ball that is keeping it in the circle. So since T is the force that is directed towards the center, but mg also has a component along the radial direction, we are always interested in circular motion, we are always interested in force components along the radial direction and the tangential direction. Therefore, any force that is not along the radial or the tangential direction should be split into those components. So therefore, it's necessary for us to split mg into components. So let's mark this angle as theta, in which case you can divide mg into two parts. This angle is also theta. So you can divide mg into two components. This will be our mg cosine theta and this will be our mg sine theta. So therefore, the net force towards the center, which is our centripetal force, must be T minus mg cosine theta. And this is equal to the centripetal force, which is, we know, mv squared divided by r. M is the mass of the object, v is the tangential speed, and r is the radius of the path it travels. But along the tangential direction, there is simply an uncancelled force. So mg sine theta is our tangential force, so we can equate it to mass times the tangential acceleration. So it is this force that is acting against the velocity because this object is moving in the counterclockwise direction. So its velocity at this instant is given like this. So this force acting opposite to the velocity will slow it down as it moves to the top. And then once it is on its way back, it will speed it up because the tangential force will be in the direction of motion, so therefore it will speed it up. So it is this tangential force and acceleration that is responsible for the change in the speed of the particle. Let's take a look at what happens when the mass is at the lowest position. So when the mass is at the lowest position right here, the forces acting on the object right now are mg straight down and T is going to be straight up like this. Notice that at this instant, just at this instant, there is no tangential component of force or tangential acceleration. So the net force towards the center at this position will be T minus mg, and that T minus mg must be the centripetal force pulling it towards the circle and causing it to move in a circular path. So T minus mg equals mv squared over r. Think about it. If at this position T and mg are going to cancel each other out completely, then you know at this time or at this instant, the instantaneous velocity of the object is horizontal. So if the net force becomes 0, then the object will have to move in a straight line. But we know that the object curves and describes a circular path. So T cannot be equal to mg, but should in fact be more than mg, such that the difference in the two forces causes an inward pull that makes it move from its tangent and describe a circle. So T minus mg equals mv squared over r. Or therefore we can write T as mg plus mv squared over r. So this value of tension is going to be the maximum tension throughout the circular path. So as the mass describes the circle, vertical circle, the tension is not constant, it keeps changing, and the tension is the maximum at the lowest position in the circle. What happens when the mass is at the topmost position? So when the mass is right here, the forces acting on the mass are again mg straight down, and then the tension in this case is also going to be downward. So I'm going to just represent by another arrow like this. So at the top position now, the tension plus mg, remember that the tension here is a different value, so I'm going to call this T2. T2 plus mg equals m v2 squared divided by r. Because the velocity here is different, remember it changes in speed as well. So because both forces are directed towards the center, the sum of the two is equal to your centripetal force, or T2 now is equal to mv2 squared divided by r minus mg. So this in fact is the minimum value of the tension throughout the circular path, because it's the centripetal force minus mg. So to summarize, in vertical circular motion, there is a tangential force and therefore a tangential acceleration that changes the speed. And in a particular example where the mass is tied to a string and whirled in a vertical circle, tension is maximum at the lowest position and minimum at the highest position. And all we do is at any position represent the forces, find the net force towards the center and equate it to the centripetal force, and the tangential force should be equal to the mass times tangential acceleration. So let's look at an amusement park ride where the cars are going around in a vertical loop. Even though this loop is not quite circular, we can approximate this to be a circular loop for our convenience. So here is what happens. When the car is here, if you look at the person, the forces on the person are, there is mg straight down, and then there is the normal force. Because the person is sitting on the seat pushes him up, there is the normal force which acts upward. So therefore, again, if the person has to describe the circle, there must be a net force pulling him towards the center. So we can write Fn plus mg equals mv squared over r, or Fn minus mg equals mv squared over r, or Fn equals mg plus mv squared over r. And we know that this normal force is the force which the seat pushes up on the person, and this is what the person experiences as a sensation of weight. So the normal force is referred to as the apparent weight of the person. So this would mean that the apparent weight of the person would be more when he's at the lowest position.